Now we're going to try to understand what the relationship between pressure and temperature is. So far we have said that at a given temperature, that the stronger the intermolecular forces of a specific liquid, it'll mean that it takes more energy to vaporize that liquid, and this will mean that the vapor pressure is smaller because there is a smaller fraction at a given temperature. There's a smaller fraction of molecules in gas form because those molecules would rather stay in liquid form because they're held together. Alright, how do we throw temperature in there? Let's start just looking at some data that you may be familiar with, such as at what temperature does the water boil? Well, that depends on the atmospheric pressure. For example, at the sea level, what you will have is what we call the normal boiling point. Normal boiling point means boiling point at 1 atmosphere. That's the pressure at the sea level. However, as you go in higher altitudes, the boiling point decreases. Okay, and we'll have to understand why. So for example, if you are in Denver, Colorado, this is your elevation, the boiling of water takes place at a lower temperature. Finally, if you decide to climb up the Mount Everest, you're boiling, the temperature, the water will boil at 78 Celsius. Okay, so almost about 20% less. So, sure, there is a relationship between temperature and temperature and pressure. Which one is that? All right, you may want to see these kind of graphs and try to understand them. In here we're plotting the curves of different three liquids. So this is the vapor pressure versus the temperature, and you will see later that this typically has an exponential form. Okay, what does that mean? This tells you already that the higher the temperature, the higher the vapor pressure. Okay, that should make sense because the higher the temperature, it is more likely for molecules of liquid to abandon the liquid phase into the gas because they have more temperature. That should make sense. And what happens when the vapor pressure is equal to the atmospheric pressure? So and that's an important thing to remember, when the vapor pressure is equal to atmospheric pressure, that's when boiling happens. This is why these are the boiling temperatures. So this is the boiling point of that specific liquid. So in other words, the vapor pressure will increase as the temperature increases until the vapor pressure is equal to the atmospheric pressure. In this case, at the sea level, it would be 1 atmosphere. In that case, that's when you have reached the boiling point. So now we should be able to read these graphs. It makes sense that the liquid with the stronger intermolecular forces, or if you will, the stronger enthalpy of vaporization, is the one that keeps a lower vapor pressure and therefore a higher boiling point. Water presents hydrogen bonds, diethyl ether presents a weak dipole-dipole interactions. Therefore, we can say that because the diethyl ether has weaker intermolecular forces than water, has a lower enthalpy of vaporization, it will have a higher vapor pressure and it will boil earlier, if you will, at a given temperature. Alright, so these points are the boiling points of each substance. Okay, so let's see if we can try to, if we can understand a little bit further with a problem, these kind of graphs. In this case, it's asking you for which one will have the stronger smell. Stronger smell just means that it has a higher vapor pressure. And let me remind you, I'll draw it again, is that the stronger the intermolecular forces, it implies that it has a higher enthalpy of vaporization. It will imply that it has a higher boiling point, and it will imply that it has a lower vapor pressure at a given temperature. Okay, so can we rank these substances in terms of boiling point, or if you will, in terms of intermolecular forces? Well, we see that this one can form hydrogen bonds, this one can form hydrogen bond, and this one can form hydrogen bond. Which of these three will have the highest or the strongest of the intermolecular forces? Notice that these are carboxylic acids. Carboxylic acids are known for being able to build double hydrogen bonds. In here, I'm gonna draw two carboxylic acids so that you can see that carboxylic acids will form double hydrogen bonds. They are stronger, so these two for sure will be the strongest of the hydrogen bonds. Which one? Well, in this case, if this is heaviest, I would say this is heavier than this one, so this will be number 1 and number 2. This is a regular hydrogen bond, methanol, so it's not double like a carboxylic. And then finally you have here two dipoles, and here I'm writing an exception. You're not supposed to predict that, but in this case, even though the ether has a higher mass, the strength of the dipole is smaller, so this is a dipole-dipole interaction, so is ether, but the dipole-dipole interaction here is stronger, therefore it overrides the mass. Again, it's tricky. We will not make you decide between when you have contradicting factors. Alright, so now that we know the ranking of intermolecular forces, what kind of curves would we see when we have vapor pressure versus temperature? Well, if we choose the most volatile, and volatility, it is the capacity for a liquid to become gas. So if we were to put it in this graph, the lower the volatility, and the lower the smell, of course. Okay, so let's start with methyl ether. In this case, you'll have the first one, and this will be your number 5. Why? Because at a given temperature, it'll be the one with the highest vapor pressure, because it's the one with the weakest intermolecular forces. Okay, let's draw this line as this is the 1 atmosphere. In other words, that's when the liquid boils. Then you'll have here number 4, and there you got the trend. Number 3, number 2, and number 1. Okay, the least volatile will be the one with the highest boiling point. It'll take more energy to vaporize.